So let's see some example applications of curve integrals. And these applications will be easier to understand if you follow the interpretation of adding properties of little segments, okay? So my first example will be to calculate the length of some curve. So how do you calculate the length of a curve? Actually, that's very easy. The total length of a curve, and it might be some crazy thing, yeah? It might even loop around itself and so on. But as long as you can find a parameterized version for this curve, it's very easy to find the length of a curve by doing the integral along the curve C of dl. And I will show you how to find dl, okay? So by integrating these differentials of length, you can find the total length of a curve. Okay, so remember, dl will just represent the length of this curve when the parameter u changes from u0 to u0 plus du. Okay, so when you increase your parameter by an amount du, you will cover a length dl. So then you can calculate dl and do the integral of dl to find the total length. I will show you how to calculate dl very soon, don't worry. Maybe you want to calculate the mass of a wire. Okay, so now you have a wire also, some crazy thing. It's a knot or something, and this is a curve in 3D space. So it's a curve R of u. But maybe this wire has a density that changes with position. Okay, so maybe the density of this wire, let's call the density lambda, is also a function of u. Okay, so the density at one end is different from the density at the other end. In general, it's a function. So then what you can do to calculate the mass, the total mass of this wire, is to sum up over the curve the different differentials of mass of each segment. Okay, and the differential of mass of each segment is simply lambda of u, which is the density, times the differential of length. Remember, this density is the density of a wire, so it's measured in kilogram per meter. Okay, it's a linear density. It's not a volumetric density, it's not a surface density, it's a linear density, kilograms per meter. Okay? So to find the mass of something of density lambda, you just multiply lambda by the length. This is true if lambda is constant. Now, if we have divided this curve into differential sections dl, then since dl is infinitely small, you can assume that the density is constant in this infinitely small interval, and therefore the total mass of this small piece is simply dl in meters multiplied by the density in kilograms per meter, such that dm is measured in kilograms. Yeah, so you add up all of the dm's and you get the total mass in kilograms. Makes perfect sense by using this interpretation. And finally, almost identically to what we did in surface integrals, you can also, for example, calculate the center of mass of this wire. And it's identical, the same exact equation. The position vector of the center of mass, and this is a vector, is equal to the line integral of r times lambda dl divided by the line integral of lambda dl, where r is the position vector x, y, z. Okay? So this is how to calculate the center of mass of a wire. So as you remember, you can get the different components. So you can split this integral into 3 integrals, each multiplying x hat, y hat, and z hat. Yeah, and so on. The same as we did with surfaces. So these would be the interpretations of the applications of line integrals. So I hope that clarified the meaning of a line integral. Okay? So thanks for watching. See you in the next video.